In the name of God, welcome back to our next session in this series about kinetic theory of gas. We have already covered 6 topics from introduction, recap of probability theory, and how probability densities are used kind of to compute averages as sum or integrations. I've given some examples which we're going to use later, and then we have covered the statistical definition of temperature, and finally we arrived into this Boltzmann factor and Maxwell-Boltzmann distributions. So today I would like to dive a bit further to talk about how one can do theoretical physics using Maxwell-Boltzmann distribution. So what we have derived earlier. The first example is going to be about something happening in the sun, okay? And then we're going to address some other properties, physical properties of gases which can be derived by using the Maxwell-Boltzmann distribution. So maybe I start with this topic. I call it Boltzmann. Let's say Boltzmann factor in the sun. Okay. The main message is that there is some sort of energy supply within the sun, some sort of reaction happening inside the sun. The reaction releases a lot of energy, and the energy reaches us down here on Earth, and we depend on it for surviving. And we're going to kind of take a look at that reaction and then address it within the context of what we have done so far, in particular using Boltzmann factor to analyze the reaction there. So I start with this statement. Maybe I take a different color. Sorry. Main energy supply within the sun is via this reaction. So it's a fusion, nuclear fission reaction. This is the main reaction. What happens is that we have 2 protons. So this is 1 proton. If I write it as P plus proton, and plus it is positively charged, coming with another, interacting with another proton to produce a deuterium, D, plus a positron, plus a neutrino of the electron type. Right. So I assume that we know what a proton is. A deuterium is a state made of combination of a proton and a neutron. So D is actually a state with proton positively charged and neutron, which is kind of neutral, combined together. So it's a kind of a state like that. And a positron is like an electron, but the opposite of an electron is positron. Neutrino is a neutral particle. We're not going to go into details of that, of what these are, as you may know them, but the main reaction is that whenever this reaction happens, it releases a lot of energy. Okay. But the point is that if you look at the left-hand side of the reaction equation, we have two positively charged objects or two positively charged particles coming together. And from electromagnetism, we expect that since they have the same charge, there's going to be a repulsive force whenever you try to bring these two positively charged particles near each other. So in order for this reaction to happen, there's going to be a big energy barrier. There's going to be a potential which kind of prevents these two charges coming together into fusing to make a deuterium state, right? So in other words, what I've just said, one may consider it schematically to be something like this. If I have an axis for energy, right, and somehow I'm going to represent the barrier for this reaction to happen to be something like a hill. So we have a hill, and the height of this hill, say, is the energy barrier. So these two protons coming together, they're going to experience some potential energy barrier, which is so in electromagnetism, we're going to have E squared divided by 4 pi epsilon naught times R. Right? So E, small e here, is kind of a unit of charge, right? We have 1 unit of charge for the first proton, another unit of charge for the second proton. If the charge is Q1, Q2, so we have Q1 times Q2 giving E squared divided by 4 pi epsilon R. R is going to be the separation between the protons as we try to bring them closer and closer to each other. So for this reaction to take place, we would need on the left hand side we have let's say 2 protons, and these protons would need to kind of cross this energy barrier for the reaction to happen. So it's kind of pictorially like a classical climbing of a hill. So you need to do some work before one will be able to reach this other side of the hill. On the other side of the hill, we can consider that the reaction would have happened, and we have a deuterium plus a positron and a neutrino, right? And so the kind of distance required before this reaction can happen is that the two protons should be really close to each other, where R should be order of magnitude like 10 to the minus 15 of a meter, right? So this is the distance which the protons must approach before the reaction take place, before the reaction happens, right? So using this order of magnitude value for R, one can compute the energy, barrier energy, the energy which is required to be crossed. It is going to be approximately equal to 1 mega electron volt after substituting the values of E and epsilon naught. You can do that as an exercise. So this is the sort of energy barrier which two protons need to cross before the reaction take place. Again, I have two protons coming towards each other, so our distance between them is going to be smaller and smaller as they approach each other. While approaching each other, they experience this energy barrier. This energy barrier, classically, if we consider it classically, if we consider the reaction in a classical manner, the two protons have to cross this hill, they have to cross this energy barrier before the products of the reactions can be formed. So you have a deuterium coming out and a positron coming out and a neutrino of the electron type, right? And if we assume that the temperature at the sun, so T sun, if we assume it's approximately 10 to the 7 Kelvin, then one can compute the Boltzmann factor. Boltzmann factor for the reaction. The Boltzmann factor for the reaction, it's a sort of a measure of the probability that the reaction is going to happen. So one can compute this. This is going to be approximately, remember, the Boltzmann factor is e to the minus e. Here, E energy is going to be the barrier energy divided by Kb, Boltzmann constant, times the temperature T. Okay? This is going to be something really, really very small, like 10 to the minus 400. So one can think of this to be probability of reaction going to happen. So what's going on? I mean, this is like zero. It's like saying that this reaction is not possible. And if this reaction is not possible to take place in the sun, it means that we don't have sun, we don't have energy production in the sun, we don't have sunlight, so boom, we're all gone, nowhere to be found. Okay, so this is sort of a contradiction in the sense that since I'm seeing the sun shining now, I'm living on Earth. Contradiction. It's sort of contradiction, or maybe our assumptions isn't really working well. So the assumption is that I'm treating this reaction to happen in a classical manner. If I assume that the reaction goes in a classical way, then the probability for the reaction to happen is zero, and it doesn't happen. So the world is not really classical all the time, and that is what saves us. And we have the sun shining. Quantum mechanics is what happened. There is something called quantum tunneling. Quantum tunneling, if I pick another, so quantum tunneling kind of is a brute force way. Let me pick my pen again, of going through this barrier. Okay, so instead of going up the hill before the reaction happens, something magical in the sense of quantum mechanics happens, where you have the process really crashing right through into the barrier and then producing the outcomes, right? This process is called quantum tunneling, and you're going to learn, or maybe you have already learned about it in your quantum mechanics or quantum physics course. So quantum tunneling is what really allows this reaction to happen, and we have energy production, so we happily living, thanks to God. And I hope this is an example you can see how to use. But well, this is a contradictory example in the sense that we used Boltzmann factor in a classical way, applied it to this reaction, but actually what's happening in reality is quantum mechanics. Okay, there are other, you can do more realistic physics. If we keep down in the classical regime, we can do, we're going to show physics that can be done using the Boltzmann factor or using the Maxwell-Boltzmann distribution. Actually, this is going to be what I'm going to describe. If we go to next page, if I go back a little bit, we have seen that given a gas molecule in a container, the probability for a chosen molecule to have a speed, so remember, a speed is a continuous variable, right? Speed can be 0 to anything, okay, anything positive. Okay? So the probability for a chosen molecule inside a gas container to be between V and V plus V. Remember, we have derived this, so probability, I'm going to choose a different color. Probability of the speed of a molecule to be somewhere between V and V plus dV. This probability, we have seen that we can write it in this way. It's a probability density function times dV, and this probability density function is the Maxwell-Boltzmann distribution. Okay, I'm tempting not to write it, but maybe for to be complete, we can write the distribution as 4 divided by square root of pi 2 kb m divided by 2 kbt square 3 by 2 to power 3 by 2 v squared dv e to the minus m squared divided by 2 kBt. So one can use this to do a lot of physics. This is what I'm going to introduce next. The thing is, we kind of pictorially, if I draw something like a box, we have a container with gas inside it. So we have molecules kind of moving randomly. Molecules, we assume these molecules to be like ideal particle-like molecules. As the molecules move around, they carry with themselves some physical properties. So if we choose a test molecule from this container, then or maybe I say choosing test molecule carries with itself physical properties, right? These physical properties are, for example, one can talk about momentum of the molecule. When one can address the energy it carries, right, etc., and some other things, let's say some flow properties. Yeah, we're going to address this in detail. So for example, this test molecule has momentum. You can compute its momentum. Average momentum is going to be mass of the molecule times average velocity. You can compute its average kinetic energy, half mv squared, so it's going to be half times mass of the molecule times the average of v squared. And whenever I talk about average, remember we compute averages using the probability distribution, and here we have the Maxwell-Boltzmann probability distribution. That's the main gist. We're going to use that probability distribution to compute various properties. In a schematic manner, I would put it this way, that one can compute flux of gas as a starting point. So if I have flux of gas molecule, so flux of gas is like number of gas molecules crossing a unit area per unit time. If I'm able to compute this, if I'm able to derive this somehow using the Maxwell-Boltzmann distribution, as we're going to see, we're going to do that. You can use that to compute, let's say, pressure. Okay, so pressure, we know that gases have pressure of gas. Yeah, this is going to be sweet. I hope you're going to see that we can derive a formula for the pressure to be some function of temperature. We have already kind of defined temperature, statistical definition of temperature. So pressure in terms of temperature and volume of the container, and maybe the number of gas molecules. So this kind of equation is an example of equation of state. Okay, and this pressure is a kind of a classical quantity, and this is something that is going to be realistic, and one can do checks using experiments. So we're going to derive this using theoretical approach. If our first step is called 0, I can derive, once this is derived, the flux of gas molecules. One can also derive pressure. Okay, so we're going to move from here to here. The same thing using the flux, we can compute something maybe I call transport properties. It's kind of generic name. There are lots of them, so this is going to be 2. Transport properties number 2. Example of this, one can talk of effusion or effusion rate. What does effusion mean? It means, for example, if I have a really small hole on one side of the container, one can compute the rate at which the gas molecules can come out of this container, and you can do it. Has applications. You can do it for separation of gases, as we're going to see later. Another property is mean free path. So as the gas molecules in the container move, let's say randomly, and they collide with one another, one would like to know what the mean free path is. On the average, how long, what distance these gas molecules are going to cover before they collide with each other, before collision, right? So the mean free path is something. One can talk about viscosity. Viscosity is a sort of friction, but instead of friction between two solid objects, we're talking about friction within a fluid or friction in a gas. One can talk about or drive the thermal conductivity. How easy or difficult is it for different types of gas to transport thermal energy from one point to the other? Another physical property we're going to address is diffusion. So for example, if one is in a big room and there is perfume released somehow in one corner of the room, you realize that with time the perfume is going to reach some other parts of the room, but this doesn't happen kind of instantaneously. It takes time, right? How the concept of diffusion can explain that. So these different physical properties, which I put them all together into this set, well, it's an approximation. Transport properties, we're going to address them kind of one by one. So the first step is to compute flux of gas molecules using the Maxwell-Boltzmann distribution. So this is going to be 0.0. I'm going to divide these into different little bits, and when you combine the little bits, we're going to see what the formula of flux of gas is going to be. The little bits, I'm going to call them A, B, C, D. So you have A plus B. So it's as easy, hopefully, by the time you see the explanations, it's going to be very easy, like A, B, C, D, right, up to point F. And the derivation for the theoretical formula of pressure of gas is going to be G. I'm going to show that in step G, and each of these ones we're going to have H, I, J, K up to L. So this is these are going to be addressed one after the other, one by one, and I hope you're going to enjoy it. Okay, I think that's it for now. Until the next session, I say goodbye. Take care.